Intimidated by having Adam here, because I think he probably knows a ton more about the stuff I'm about to talk about than I do myself. But in the day job, I help people make networks in the cloud built out of VPNs. And in past life, I did security stuff at banks. And so I've got some passing familiarity with security protocols and their implementations. And as a tinkerer with Internet of Things stuff and open source hardware, I've kind of tried and failed and found out the hard way that some of the things I'm about to talk about can be quite difficult. So, just like a good blog post, I would hope, I'll give you the sort of too long didn't read version right out from the get-go. So, if you're trying to do security protocols like SSL or SSH or IPsec, and you're trying to do those with a regular Atmel-based Arduino, then you're going to fail because you just cannot fit the protocol stack into the constraints of that device. And I'll go into a little bit more detail later about why that is. But the main constraint is RAM. You've got 2K to play with on those low-end devices, and 2K just ain't enough. The sort of amber zone here. So if you're trying to do security protocols in a mid-range to high-end embedded device, then that's feasible. You're going to be able to do it. So pretty much anything that's got an ARM CPU in it, the software stacks are available there. You've got enough horsepower. You've got enough memory and other things in the environment that you're going to be able to actually make an implementation work, but some heavy lifting is involved and your mileage may vary. So it's by no means easy. If you're running on anything that's got a full Linux stack, even an embedded Linux stack, you're probably most of the way there. But if you've got a full Linux stack with a package manager, you are home and dry. It's easy. You've got all of the benefit of everything that's already been done for all of the PCs and servers. So here's what I'm going to run through. I'll look at the anatomy of a typical security protocol. I'm going to look at SSL in a little bit more depth than the others. And look at the key exchange dance that goes on within that. But we'll briefly look also at SSH and IPsec, and that's really just to illustrate that you get the same kind of key exchange dance and pretty much the same thing going on for all of the different security protocols. I'll talk about how Linux basically makes things easy and what goes along with Linux to make those things good. I'll then take a look at libraries and the ecosystem that's there around higher-end microcontrollers. And then I'll finish up by explaining why ordinary Atmel Arduinos just don't quite cut it for this stuff. So which protocols am I talking about? Well, it's what I always used to refer to as the S protocols when I was doing the banking stuff. So secure sockets layers, which, of course, we all still talk about it being SSL, but in reality these days it's more often actually TLS, so transport layer security. Secure shell, SSH, and internet protocol security, IPsec. Yeah, that's legible, thanks. So this is what the SSL handshake looks like. And so the blue stuff that you've got at the top of that diagram, that's just your TCP initiation, so getting the protocol below SSL going. But once we're into the yellowy orange that you see on the screen here, this is what's going on within SSL itself. And I'll put these slides on SlideShare afterwards, so you should all be able to actually read it in a bit more detail. And there's some links at the end of the deck for further reading. So the client's going to connect to the server, and the client's going to say, hello, these are the protocols that I know about. And these are the ways that I'm going to be able to continue with a conversation. And this is actually often where some of the trouble starts, because the server's then going to reply with its hello and say, well, these are all of the cipher suites that I support, and here's my certificate and various other things. And it's at that point that you hit the question of, am I going to a lowest common denominator for my secured conversation, or am I going for a highest common factor? Now, you'd think security engineers would go highest common factor. It's kind of let's pick out the cipher suites, the protocols, and everything else to be as secure as we possibly can. And sadly, when you look at real-world implementations of a whole ton of this stuff, an awful lot of it falls down to lowest common denominator. And so you've got servers out there that are supporting really weak protocols in order to deal with really ancient browsers. And then when your modern browser rocks up and says, yeah, I support all of the brand new stuff, the server says, well, let's still have a conversation on this really ancient protocol with a whole bunch of known vulnerabilities in it. And it's also the range of those protocols that becomes something of a problem if you're doing an embedded implementation. So if you're running a browser on a desktop, then you've got a ton of resources these days, and you're going to be able to support every cipher suite under the sun. If you're building a web server and you're intending to be able to serve all of the different browsers out there, or maybe everything except IE6 because it's just too awful, then you're still going to have all of the resources that you need to support all of the different cipher suites. But when we look into the embedded environments, you're going to get a little bit more resource constrained there because you might want to reduce down that list. So the client said hello and said what it can deal with. The server said hello back and said what it can deal with. And hopefully some agreement can be reached there. And whether it's lowest common denominator or whether it's highest common factor, the conversation then moves on into key exchange. So a pre-master secret's going over from the client to the server. There might then be session key generation going on as well. And at this point, the client sends its final packet and it's finished with the process. All being well, the server's then sending its final packet back, and they're ready to now reach the bottom and they can start exchanging messages in ciphertext rather than in the clear. So here's a packet capture of the client hello. And I've put this up on the screen merely as an illustration of the verbosity of some of these messages. So you'll see that it's truncated. There's a scroll bar on the side there from the screen that this packet capture was taken from. So that screenshot isn't even a complete client hello for a relatively typical session. So the size of that packet will give you some indication of the complexity that lies behind sending that packet. And this is the one, remember, where we're just listing out the cipher suites that we're willing to talk in. It's not actually the packet where you're getting into the key exchange itself. So I could have bored you with screen after screen of packet captures from the ongoing conversation, but the point is it gets quite verbose. So it's a very similar story for SSH. Begin by establishing the TCP connection first. Then you're going to have a message from client to server saying which SSH protocol version it supports, and a message back saying which protocol version it's going to support. Then you get into the key exchange initiation, and then the key exchange itself takes place. And then once you've got to the end of the key exchange process, then you can actually do the service request and start doing the SSH shell session and any tunnels that are running across that. And IPsec, you're going through pretty much exactly the same dance. So you'll see sort of different labels for some of the parts that are going through here. But broadly, it's about the same number of packets bouncing backwards and forwards in order to firstly establish an exchange of keys between both the client and the server, and usually some sort of agreement about protocol suites relating to those keys. And then session keys are established, and then a secure conversation can be established following from that. So the green zone. Linux makes this easy. If you're doing stuff with a Raspberry Pi or a BeagleBone Black or even an old BeagleBone, or pretty much anything that can support a Linux suite, and especially one that's got a package manager on it, then you can just reach for your package manager, say apt-get install, and then you reach out for OpenSSL, OpenSSH, or OpenSwan. No relation. And once you've got those packages, you've really got the full support of the entire cryptographic part of the Linux community stood behind you in order to either have integration into things that you would want to do. So whichever language you're then programming in, there's going to be APIs available into those packages which you can use for secure conversations. It's pretty much ubiquitous. And when you're looking at something like IPsec, then a lot of these things can be established at a system level. So it's almost irrelevant then how you're developing your software, because the secure conversations can be done underneath the application and they become pretty much transparent. So when you look at the economics of this, BeagleBone Blacks are 35 quid or whatever they are these days, can actually be cheaper than Arduino Ethernets. So it would sort of encourage you towards a path where you just kind of go, okay, I'm going to run a full Linux stack because I can get all of the security stuff easily and for free to go with that. So, as I said at the beginning, things start to get a little bit trickier with embedded. So, if you're doing embedded, then you're going to want a security suite library. And there's a bunch out there. So you've got things like Polar SSL, Wolf SSL, and Matrix SSL. And if you go along to their websites, as I've kind of highlighted here, you'll see all of them making grand claims about how they fit into small environments. And small is a bit of a moving feast here. So Wolf SSL is claiming a runtime memory footprint of 1 to 36K. It's kind of, I'd love to see the code that actually does a 1K runtime footprint, because that really would be super lightweight. Matrix SSL says less than 50. I think that's a lot more realistic. And Polar SSL says as small as 30. That's a bit like those sale signs that you get in shop windows, which says up to 40% off. What does that actually mean? So the point there is, all of these things can actually fit into relatively small footprint devices, but compromises have to be taken in order to do that. So if you're really, really tight on memory, you're probably getting yourself down to you're only going to actually use one cipher suite. So when that conversation's going on of cipher suites accepted on one side, cipher suites available on the other side, you're kind of pinning yourself to one, and you're taking the consequences of that. So if you're maybe running a web server on this thing and you've got browsers coming along, you're going to have to pick something that most of the browsers work with, but that's probably going to stop you from picking a genuinely secure protocol. If you're doing machine-to-machine, then if you're in the fortunate position of you're controlling both ends of that conversation, it's all good. You can pick the suite that satisfies your threat profile, and you're off to the races. I've got some links at the end which kind of dive into people that are doing for real work with some of this stuff. And so you can go there, see some of the code samples. It's not terribly grisly, but it's certainly not entry level. So we're a good couple of steps of sophistication beyond the kind of thing where people are taking processing for the Arduino and just copying chunks of code into a sketch and pressing compile and it's all good. We're talking about a level of competence where people are setting up their own tool chains and they're quite happy wrangling the C++ compiler for themselves. So that's kind of the skill entry level to doing this kind of mid to high range embedded with security protocols. So you've got trade-offs that you can do within the stack there. And if we're looking kind of through the stack, you've got a certain amount of resources are going to be needed for your client application, certain amount of resources that can be taken purely for the encryption piece of it. And then don't forget, you're probably going to have a TCP, well, you must have a TCP stack underneath that, and that's going to take some resources. And you're probably going to have a real-time operating system type of stack underneath that, so that you're not having to code completely everything against the bare metal. So the keys, the key mangling, it's not going to fit into 2K. So 2K is what you get on a regular Arduino or something like an Arduino Ethernet, or pictured here, a nanode. I've recently been doing some tire kicking with the nanode, and one of the things I found there was you'd struggle to get an MQTT library running on there, along with a one-wire library, along with the TCP stack. And so I'm hitting issues where as soon as you actually try to do any work with all of those things loaded up, then you're kind of hitting out of memory errors and everything starts to go wrong. Maybe not instantly. You can end up with those really uncomfortable situations where it works for half an hour or so and then poof, goes away. So there's definitely no space left to be able to add in a security protocol on top of your networking protocols and any messaging protocols or web serving or whatever else you're trying to do with the device. So this is a bit of a shame. It's kind of, it feels at the moment that we're at the birth of a big thing with Internet of Things and open source hardware from hobbyists driving that. And there's really no easy access on some of these hobbyist things for secure protocols. So we're going to be back to square one in terms of everything will be no security by default. We can't take the secure by default route in the early days of this stuff. And we've seen that story before and know that it ends pretty badly. So back to my summary. Sadly, the kind of low-end, easy access hardware isn't providing the necessary resources to run the protocol stack in order for us to use things like SSL, SSH, IPsec. Once we get into sort of ARM-level hardware, then it becomes feasible. But the present state of the art is you're having to do manual wrangling of relatively complex security libraries in order to make use of that. So it's not the point-and-click experience that most hobbyists are accustomed to at the moment. As soon as you get into something like a Raspberry Pi or a BeagleBone Black and you've got a full Linux environment, and there's some of the Arduinos now have kind of got a Linux bit alongside of them, then you've got the benefit of all of the heavy lifting's been done for you with the protocol suites and packages around that, and your application can take advantage of the APIs that integrate into those or the operating support that sits on top of those, and you're off to the races. So I'll pause there for any questions. Andy.
Hi there. That was brilliant overview. I'm wondering, even if you've got your BeagleBone and your Linux on, how much extra do you have to pay for the hardware to get enough entropy and randomness to keep it secure?
So there's some really interesting stuff going on with that at the moment. Even the relatively low-end ARM system on chip tends to have stuff in there to do hardware randomness. So it's often been bundled in as part of underlying hardware support for crypto protocols for mobile phones and set-top boxes. This might be the one good thing about DRM, is when you're getting set-top boxes that have been derived from, when you're getting socks that have been derived from set-top box product lines, then they've thrown in a whole bunch of crypto capabilities to support DRM. And yeah, they've made that stuff fast, so it's not getting in people's way. There's projects I'm seeing starting to emerge where people are using Raspberry Pis as HSMs. And there's some folk I know are doing a presentation next week at RSA about that. So it's all a little bit scary biscuits, but
Do they have access to the stuff that a normal Raspberry Pi user can't get to, like the binary blocks for the...
Not to the best of my knowledge. So I think they are fumbling around in user land with just the documentation that has been exposed to everybody else.
I want to say these are certified flips.
Paul, you can have.
Yeah. I know some people who work with PIC quite a lot,
Yeah.
and I don't. But what they tell me is that there are PIC chips at the quite the low end which have enough on them to be able to do SSL. I just wondered if you'd come across that. What I wondered is what they left out in order to, what's left out in order to achieve that.
So I think I could almost translate that question into where does the line lie? So if 2K SRAM on a regular Atmel Arduino isn't enough, then what is? Is it 4K? 8? 16, 32? I think when you get to about 32K, you're probably in a position where you could do something really basic. So at that stage, I think you could take some of the lighter weight cipher suites and lower key lengths and actually have a practical implementation. So my sort of best guess here is 32K feels about right as a de minimis.
Do you think they probably have to make some sacrifices though as to which?
Oh, you're definitely making sacrifices because you're choosing less secure cipher suites and you're definitely having to choose shorter key lengths because just the practicalities of it. If we're thinking about typical key lengths that get thrown around for these things, people start talking, actually people express the key lengths in bits, so you do need to remember that you can divide by 8 and it's not actually that many bytes. But even so, you're going to end up having to compress your key length and you're therefore going to have a compromised overall implementation.
Can I just, I'll take you out. The question for me is, one of the problems is you define that this software has been written for big machines.
Yep.
And there's always a trade-off in software between speed and size.
Mm-hmm.
I mean, how much have people gone down the route of, let's take the code, but actually optimize for small amounts of RAM? Because actually these small machines typically have vast amounts of flash, so you've got plenty of code space, it's just RAM that you're short of.
So, and this is where the embedded libraries do actually help. So things like Polar, they've done as good as they can almost to put things in flash and not actually bash the SRAM. And I think the other thing related to that is where are you seeing hardware support for some of the algorithms that are being dealt with in the cipher suites? So a lot of the higher end ARM chips now will actually have hardware crypto support on them. And if you're taking advantage of that, even if you've got a relatively weak CPU, which would mean it would take time to do all of these key exchange processes, that stuff can be accelerated in hardware.
I'm a fan of QNX, which is like a Unix without the Linux kernel, and you rebuild it dynamically, so it's very lightweight, very good to be able to audit that. And the question really is you glossed over the compilers,
Yep.
and presumably with a lightweight chip, you could probably audit that as well. But it's going to get to be impractical to audit a large chip with a full Linux.
So in terms of auditability, and especially somebody made a joke about FIP certification a moment ago, but when you get into the question of certifications, one of the things that you can benefit from there is BSD, actually more so than Linux, has been audited up the yin-yang as a substrate for security functionality in an awful lot of commercial appliances. So the auditing has taken place of those code bases. Yeah, absolutely. One of the things that's starting to emerge is stuff like Mirage OS, where you can create essentially mission-specific microkernels using OCaml. So it ends up being very similar to the QNX approach. And the difference there is QNX is going to benefit from the fact that you've got a C++ toolchain that you can benefit from, whereas the Mirage OS stuff, they've gone down the OCaml route, and it's in some ways more computer science-y, purer, but it also means kind of having to start from scratch on a whole bunch of things, including the security protocol implementations. But that's going to happen anyway, because one of the whole purposes of having mission-specific sort of hypervisor kernels is to actually do some of the security functions. And they're certainly being considered for trusted execution, so where you're taking a hardware trust anchor and having parts in the way.
Thank you. I might get some pointers.
I had a question at the back there.
Yeah, so you touched briefly on the crypto support in hardware on the more modern ARM chips. How much does that actually help? Because typically what I've seen there is that they support AES in hardware, which I can imagine speeds up the actual exchange of messages. But
Yeah, so your mileage may vary. The choice of capabilities that you get there is very much driven by the sort of mission profile that the SOC has been designed for. And I think when we look at a lot of the stuff that's finding its way into sort of hobby land with the dev boards and things like Raspberry Pi and BeagleBone Black, those SOCs, typically the mission that they were designed for was something specific. So they talk about the Raspberry Pi being a mobile phone SOC. I don't believe that for a moment. Everything about it screams set-top box to me.
The Sky Go box is running the same chip.
Yeah. So, as I mentioned earlier, where you've got something that was intended for a set-top box that was going to be supporting DRM, then you might very well end up with a broader range of accelerated cipher suites being chosen to go into that SOC in order to satisfy that mission.
We'll take one last question from Errol, then we're going to switch over to the next talk. So.
I'm sorry if you covered this. I was playing with my slides during the portion of your talk. I do apologize. But for the Raspberry Pi, has any of this been fed back to them? Because I don't know the Arduino folks, but I do know them in terms of, and is this an issue for Raspberry Pi as well? Like if we had hardware support?
So this is kind of a non-issue for Raspberry Pi because Raspberry Pi is in the green zone because you can run full stack Linux on it. Right. If you are being particularly adventurous with the Raspberry Pi and sort of doing their own code your own OS and starting from scratch, then you would start to run into some of the questions that were being raised around the HSM Pi of how much have they got visibility into the non-open blobs within the CPU microcode. And sort of some of that stuff's been opened up by the Foundation. The Foundation's taken a pounding, actually. People have been kind of saying, oh, Raspberry Pi is not open source hardware like Arduino is. And I always sort of refer back to the toaster project on this. I don't know if you've seen that book, but somebody decided to make a toaster from scratch. Like he mined his own iron ore. And the point that I make here is you don't want every open source hardware project to turn into the toaster project just to have full openness. So it's kind of, Arduinos are made out of other people's intellectual property from Atmel and ARM and whoever else. And Raspberry Pis are made out of other people's intellectual property from ARM and Broadcom. And some of the Broadcom stuff has been somewhat hidden behind a veil. And I think for 99% of the time, it doesn't matter.
Struggle as well between the Foundation and Broadcom sometimes.
Yeah, and they've opened up some of the GPU stuff, which was what most people were bleating about.
Yeah.
There's still stuff around codec support, and there's probably more around security support that hasn't.
What would it be in terms of security and stuff? Just one thing.
I don't have a bleat about Raspberry Pi, so I've talked to Eben about various things, and it's sort of it's nowhere near the top of my list.
So it's more the microcontrollers.
Yeah.
Okay, thank you very much, Chris. The conversation carries on in the pub after.